Yeah. So, but and I hope you have seen all your scores, etc. So the first one, first question was about whether the ring is a PID or not, and you had to give a brief justification. So I wasn't really looking for long proofs there. You could cite any result sort of proved in the class. So so maybe something longer than what I have written, but not too long. Yeah. So Z mod 57Z is not even an integral domain. So it can't be PID. PID by definition is an integral domain where every ideal is principal. And then Zx mod 53 is same as Z mod 53Z X. So it's a polynomial ring over Z mod 53Z, and Z mod 53Z is a field. So polynomial, so we have already seen that polynomial ring over a field is in fact a Euclidean domain and hence a PID. QXY mod X minus Y, this is isomorphic to QX, yeah, where you send Y to X as well. So they are these two, this ring is isomorphic to QX and hence again it's a PID by the same result. We saw in the class that Zi is a Euclidean domain and hence it's a PID. Here the Euclidean norm is the usual norm. Yes, the usual norm itself is a does the trick. And Z pi is isomorphic to ZX. So this to prove this, we assume that pi is transcendental. So I guess you can use the result that we showed that Z pi is isomorphic to ZX. And then ZX we know is not a PID because, so there are many ways of thinking about it. For instance, polynomial ring over something which is not a field, or you can say that 2 comma x is not a principal ideal. Yeah. And in question 2, one has to check whether the two rings are isomorphic or not when in two different cases. And in both cases, they turn out to be not isomorphic. So unfortunately, there was a typo that led to this situation. But anyway, it was prove or disprove. So there's nothing wrong as such with the question. But if so, I wanted x squared minus 4x plus 4 to be there on the question paper. But since it was minus 4, both of them turned out to be non-isomorphic. Otherwise, the first A would have been isomorphic, and so you would have to prove that it's isomorphic, and in B you have to show that it's not isomorphic. But nevertheless, in B it is sort of straightforward why it's not isomorphic, and the same logic would have same argument would have been okay even if we had x squared minus 4x plus 4. The point is when you are doing over Zx and you are inverting 3x minus 6 and x squared minus 4x minus 4, so 3 gets inverted in the first setup, right? Because 3x minus 6 is 3 times x minus 2. So 3 gets inverted. But 3 has any ring homomorphism from this ring to the other ring, 1 will go to 1 and hence 3 will go to 3, right? Because 3 is 1 plus 1 plus 1. So, so 3 has to go to 3. But in the left hand side ring, 3 is invertible, but in the in the other ring, sx square minus 4x minus 4 adjoint zx, 3 is not invertible. Yeah, because we know in fact, so 3, for instance, does not divide this, or we know how every element looks like here. It's some polynomial with integer coefficient over some power of x square minus 4x minus 4 in the denominator. And such a thing cannot be equal to 1 over 3. Yeah, so you can't get 3 in the denominator in any way. Okay. So that tells you that this ring is, so there can't be any ring homomorphism. So any map like this cannot be an isomorphism. Yeah, you can't get, you can't cook up a map which will send 1 by 3 to anything. Yeah, so there is no ring homomorphism in fact. other than the zero map. Yeah, so one will have to go to zero otherwise. So that's not a ring homomorphism in our definition. And for A, the thing is, they are again not isomorphic. The point is 3x minus, in one ring, 3x minus 6 gets inverted in QX, and the other one, something else gets inverted. And you can argue that you can't find a map. So again, one has to go to one, and that will tell you that integers and this ring homomorphism sends every integer to itself and every rational number to itself. So any ring homomorphism will be identity map restricted to Q. And then you argue where would 3x minus 6 go? So 3x minus 6 has to go to a unit. And that unit has to be different from non-zero rational number in Q, right? Because or rather any unit is of this form, r times x square minus 4x minus 4 power n. Yeah, because any element looks like px over this guy, and such an element will be a unit if px is of this form. So this will be a unit if it's inverse. You can write it in this ring. So if you can write the inverse in the ring, then px has to be of this form, because in the denominator you only allow powers of x square minus 4x minus 4. Yeah, and that tells you that any unit is of this form for some rational number r, non-zero rational number r. And then from there, if n equals 0 is not possible, because then phi won't be injective. Some rational number also goes there, and 3x minus 6 also goes there. And if n is non-zero, then also you get some contradiction. So then you show that x is not in the image of phi. Okay. But if it was x square minus 4x plus 4, then you would get an isomorphism, because 3 is already inverted. Yeah, and remember x square. Note that x square minus 4x minus plus 4 is just x minus 2 whole square. Yeah. So so then you can use the universal theorem of localization to give a nice map between the two rings and show that it's an isomorphism. Okay. In the other scenario, A would have been an isomorphism. Any questions on the quiz? Okay, so let's. So I'll skip the quiz part. Yeah, I mean, I suppose most of you may have seen this, so I'll just get to today's discussion about. So till now we have seen localization and so on. So remember in the homework there was a problem that if you take a PID or a UFD, and then its localization is also a PID or a UFD. So in that sense, localization behaves well. Yeah. So if you invert some things, then it doesn't change the nice properties of the ring. It only improves in in some sense. So that I don't want to say much, but at least we know that localization of a PID is again a PID, and localization of a UFD is again a UFD. Yeah, so that reminds me, so maybe I'll do it here. So there was, so if you have a PID, so last time I think someone had asked and we ran out of time, so I didn't answer that. So if you have a PID, R is a PID, and P is a maximal ideal. So in other words, a non-zero prime ideal. Then remember R localized at P is same as S inverse, or maybe let me not introduce new notation. R minus P, which is what I think of as inverse R. Yeah, so you invert elements outside P. This is again a PID by that homework problem. Yeah, and local. So they have all the properties of being a valuation ring. Yeah, so this is valuation ring. So PID local ring is another way of thinking. So it's a characterization of valuation ring. So RP is a valuation ring. So in fact, one can write down what the valuation will be. Let me take a pause. There's someone at the door. Okay, sorry about that. So let's. So what will be the valuation? So the valuation here is, you take the maximal ideal. So R is a local ring and a PID. So you think of it as so we are in this setup and say P R localized at P is generated by X. And then you take the valuation from, so first you have to, so I'll not detail the whole process. Yeah, so you have to give the valuation of X to be 1 and valuation of X square will be 2 and so on. Yeah, valuation of X power N to be N. Yeah, and so if you take any element in R, X belong, I'm sorry, A belongs to R, then if you just check, so A has to belong, so A will belong to R. So you have this, R contains P, contains P square, and so on. Yeah. So it has to belong to, so there exists N such that A belongs to P power N, but not in P power N plus 1. Yeah. Then you decide valuation of A is just N. Okay. So if A belongs to P power N but not in P power N plus 1, that means P power N, remember, is the ideal generated by X power N. Yeah. So then A is, you can write it as X power N times B, where B is not going to belong to X. Yeah. Otherwise, so B is a unit. Okay. So this way you can give valuation to everything in R. And then you extend this to the whole field, so fraction field. So if A over B belongs to K, then you know what the valuation of A is, so you know what the valuation of B is. So valuation of A over B, you declare it to be valuation of A minus valuation of B. And you can show that this is well defined. So remember, A over B may be equal to A prime over B prime. So there's something to check. And then one just checks that this is indeed a valuation. Okay, so this is how you can show that this is indeed a valuation. Okay, any questions? Okay, so let me get to.
Excuse me, sir.
Yes.
So this property is very generic, right? We don't need RP over here. We can just have any ring such that it is a PID and a local.
Yeah, precisely. A local ring which is a PID is a valuation ring. Okay. So local PID and valuation ring is
Sir,
a thing. So that's what I have sort of proved here. Yeah.
Okay, thank you, sir.
You're welcome. So you'll see more characterizations of valuation ring later on. Okay, so now let R be an integral domain. So now we are moving towards Gauss lemma. Yeah, so we'll see a proof of Gauss lemma today, and then we will use it to show that when R is a UFD, then the polynomial ring over it is also a UFD. So that will complete the UFD section of us. Okay. So let R be an integral domain and fx in Rx be a non-zero polynomial. Then the then the content of f, which we will denote by Cf, is defined to be the GCD of all these coefficients, an minus 1, and so on. So these are elements of R. So we can take the GCD, and so one should. So this makes sense whenever the GCD exists. Yeah. So so maybe one has to put it so which admits GCD. So for instance, a UFD will be fine. Note CF is defined up to an associate. Yeah. So we don't have a unique GCD. So we say so there could be many possible GCD, but any two GCD will be associate. Yeah. Yeah, and one thing I must, so last time when we discussed GCD, we talked about GCD of two elements. So for n elements or arbitrary number of finite number of elements, GCD is an element. So the definition of GCD is D is the GCD if D divides each of them, and if D prime divides AI, then for all I between 0 and n, then D prime divides D. Okay. So that is what GCD is, and so now so I forgot to write here Gauss's lemma. So there are many versions of Gauss lemma, and the first version is let R be a UFD and fx and gx be two polynomial in Rx, then content of f times g is same as content of f times content of g. So you should think of it as these two are associates. Yeah. So of course everything so content of f times g is also content of f times content of g up to associate.
Sir, would you please repeat that part about associates?
Which part?
You said that we should think of them as associates. I didn't understand that.
You didn't understand the definition of GCD or the content? You want me to go back to content, right?
You said that, no, sir. In the in Gauss lemma, you said that we should think these associates. I didn't understand.
Yeah, so F times G. So if you take the GCD of the product of these two polynomials, F times G, that is going to be also the you take and you take the GCD of all the coefficients of F and GCD and a GCD of all the coefficients of G, and you multiply them. Then the two GCDs are going to two elements you get are going to be associated. That's what it means. Yeah. So so another way of thinking about this is if D is GCD of coefficients of F times G, and D1 is GCD of coefficients of F, and so the point is GCD is only defined up to a unit. That's why one has to think of it this way. Yeah? So this equality will never be on the nose. So there will be always a unit. Then so the thing is D need not be exactly equal to D1 and times D2, but because any two GCDs are not necessarily equal, but what you can say is D is associate of D1 times D2. So you can say, for instance, D1 times D2 is indeed a GCD of F times D. Yeah, that is something which you can say. Okay, does that make it clear? Okay. So this is the first version. There is another version which is probably more useful.
Yes,
say that again. Okay. So let R be a UFD and K be the fraction field of R. Let Fx in Rx be such that the content of F is 1. Maybe content part is not needed. Anyway, we'll see. If Fx is Gx times Hx for some G and H in Kx, then Fx you can write it as capital Gx times capital Hx for some Gh in Rx with G equals degree G, and degree capital G equals degree small g, and degree capital H equals degree small h. So there is a typo here. Yeah. So if you can, so it says that you can factor, if you can find the factors of a polynomial in Rx, such that the factors maybe are in this may have coefficient in the fraction field, not necessarily in this ring. So you expand your ring to Kx. So remember, Rx is contained in Kx. Yeah. So suppose you can factor it in Kx, then you can factor it in Rx by the same degree polynomials. That's what the content of version 2 is. Okay. And I don't think we need content F. Yeah. So maybe I think we can get rid of this. I wrote it before the puja break. So, okay. And as a consequence of this, immediate corollary of this is that if R is a UFD and K is the fraction field, like in the above setup, a polynomial Fx in Rx of content 1, that means the GCD of all the coefficient is 1, is irreducible in Rx if and only if Fx is irreducible in Kx. Okay. So there is a name for polynomials of content 1. Yeah. So maybe I'll just find that name here. So a polynomial of content 1 is called a primitive polynomial. So sometimes people use this terminology. Anyway, so maybe not that popular as such, but so for instance, Dummett and Foote uses this terminology. Okay. So let me just prove this corollary first using Gauss lemma, and then we will maybe prove version 1 implies version 2, and then finally we'll prove version 1. Yeah. So these version 2 and corollary are more interesting. This content is some technical statement. So we'll go down this route. Yeah. So this corollary you can see is quite important, right? Because it will it reduces the problem of checking whether something is irreducible in some complicated ring to some ring which is a PID. KX is a very nice thing. Yeah, it's just a PID. It's much better than a general UFT. Yeah. So one direction is sort of doesn't use Gauss lemma. So if fx is reducible, so we will show that if fx is reducible in Rx, then fx is reducible in Kx. So this direction, so we will prove fx is reducible in Rx if and only if it's reducible in Kx. So contrapositive. Yeah? So I don't know. This is maybe the backward direction in some sense. Yeah. So fx is reducible in Rx, then fx is reducible in Kx. So fx is reducible in Rx means fx you can write it as gx times hx, where g and h are some polynomials in Rx, and they are non-units. Yeah. Reducible means you can write it as products of two non-units. Now the content of f is 1, yeah, and g, h are, so that tells you that g and h cannot be constant polynomials, right? Because if g was constant, then the content of f will be g times content of h, and that can't be a unit. And that can't be 1 because g is irreducible, right? So that tells you that g and h cannot be constant. Make sense? So we are assuming content of f is 1. So g and h cannot be a constant irreducible element of Rx. It has to be a polynomial. Yeah.
Huh?
Say that again?
Sir?
Yeah.
Can you explain why they're not constant again?
So if g was a constant, so some element of R, yeah, then it's also irreducible. So content of f will be g times that irreducible element times content of h. Yeah. So in particular that constant will divide. So that constant will divide the GCD of each of the coefficient of f. Yeah. And that constant is irreducible, so it can't be 1. Yeah. Irreducible,
Yes, understood.
non-units.
Yeah, thank you.
So that's why it can't be constant. So g and h are not non-constant, and once you have that g, h, and g, so here we are not really using Gauss lemma. We are just using the fact that if this is constant, then it has to divide each of the coefficient of it. Yeah, no Gauss lemma is used, and hence they are so once they are non-constant polynomials, they are non-units in Kx as well. Yeah. Sorry. So yeah. So Gx and Hx are polynomials in Rx, but they are and Rx is contained in Kx. So they are elements of Kx as well, and they are non-units because any non-constant polynomial in Kx is a non-unit. Hence, fx is reducible in Kx as well. Yeah? So this proves that fx is reducible in Rx, implies fx is reducible. Is that clear? So once you have a factorization in Rx, you argue that if content is 1, then that factorization is a factorization by two non-constant polynomials. And then, of course, if that is a factorization in Rx, it's a factorization in Kx as well. And hence, because K contains R, and hence Fx is reducible in Kx. Okay, and for the other direction, we need Gauss lemma. So conversely, say Fx is reducible in Kx. So you can write Fx equals Gx times Hx, where G and H are non-constant polynomial in Kx. Then we argue about using the Gauss lemma. So content 1, here we even have content 1, but that is, I don't think is important for this direction. So then by Gauss lemma, Fx is reducible in Rx, because you can write Fx as so remember, Gauss lemma tells you can write it as Gx times Hx, where G and H has same degree as degree of G and degree of H. So they can't be units. Yeah. So non-constant polynomials have no chance of being a unit. Is that clear? The proof of the corollary, assuming version 2 of the Gauss lemma. Okay, so assuming this is okay, let's move to version 1. Version 2 implies version 1. Okay. Or rather, version 1 implies version 2, and then we will prove version 1. So version 1 implies version 2 is also straightforward. So so what do we have? So we will be given a factorization in Kx, and we want to come up with a factorization in Rx. Yeah. So let Gx be given by this polynomial. Gx is of this kind, and sorry, so this part of it is missing. So let Gx is of this kind, Bm power x power m, Bm minus 1 power x power m minus 1 plus B1x plus B0. And Hx is similar, Cl x power L, Cl minus 1 x power L minus 1, and so on, C1x plus C0, where B's and C's are in fraction field K. Yeah, so it's not in R, but in K. Okay, so Fx is G times H, but so coefficient of F is in R, but coefficient of G and H are in K, not in R. Yeah. But we can collect, so these are some fractions with so these K is the fraction field of R, so we can collect the denominators. Yeah. So by collecting the denominators of these things, we can find B and C in R. Yeah. So each Bm, you can think of it as Bm is some Bm prime over Bm double prime, Bm minus 1 is Bm minus 1 prime, Bm minus 1 double prime, and so on. And you just multiply all the denominator. Yeah, that's what. So maybe I can write it down here for one example. Right, so say Bm is or in general, say Bi is Bi prime over Bi double prime, Bi prime and Bi double prime. So we can find such guys in R. Yeah. So then we can take the product of the denominators. So B is just product of Bi double prime. I equals 0 to m, and similarly C. Okay. So this will be an element of R, And if you multiply by b, then what you get is something called g1x, which will have all coefficients in r. Yeah, because you have cleared out the denominator. So b times bm is, for instance, is in r, and b times bm minus 1 is in r, and so on. So g1x is b times gx is in rx. And so b, remember, is a non-zero element. We are multiplying something in the denominator. Yeah? And similarly, h1x, you declare it to be c times hx, and they are in rx. Yeah? And what we get is b times c times fx. So we use the original equation given to us, fx equals gx times hx, this equation. Yeah. So we multiply bc both sides, then we get that bc times fx is g1x times h1x. So maybe I should have written in rx. So maybe I should have added this equation somewhere. And so this happens since fx equals gx times hx. Yeah. So from this and the definition of G1 and H1, we get this identity. Okay. Now, what does version 1 tells us? Version 1 tells us that content of left-hand side is same as content of G1 times content of H1. Yeah. And what is content of left-hand side? It's BC times content of F. So whatever the GCD of the coefficient of fx is, you just multiply it by bc, and you get the GCD of this new polynomial, bc times fx. Yeah? So version 1 tells us bc times content of f is content of g1 times content of h1. Yeah. And what is okay, so now a little more notation. So G1x, we can write it as content of G1. So you take all the coefficients of G1, yeah, and take the GCD. So we can write it as, so G1 and H1 will not be our polynomials. We'll have to modify it a little further. We may have multiplied by something more. Yeah? So what you do is, so you look at the GCD of all the coefficients of G1. Yeah, G1 is a polynomial in Rx with coefficient in R. So you can factor out that GCD, which is same as the content of G1, and what you'll get is another polynomial, and this polynomial is also in Rx. Yeah. So in G1x, we can write it as content of G1 times some polynomial Gx in Rx. And H1x, you can write it as content of H1 times some polynomial Hx in Rx. Yeah? In fact, and then you know that in fact the content of G and content of H will be 1, though it's not important for this. But you can always write it this way. Yeah? You factor out the GCD part. And Fx also, you can write it as content of F times capital Fx for some Fx in Rx. Now this identity, BC times Fx times G1x times equals G1x times H1x, this you can again write it using this new polynomials. Yeah? So you get BC times CF, so little fx you replace it by CF times Fx, and G1 you replace it by CG1 times Gx, and H1x you replace it by CH1 times Hx. And you get this. Yeah. So the content part, B, C, and content F, and C, G1 and C, H1 are elements of R, and the rest are polynomials in with coefficient in Rx. Okay. 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 Good. So yeah. So as I said. So the proof of version 1 implies version 2 was more or less complete. We just multiply by content of F to get this identity. And then the Gauss original result was not about UFD, but about Z, R replaced by Z. And you get this. Yeah. So let's get to proof of version 1. So I may go a little over 12:30, but I hope there is no class, so it doesn't matter. Yeah. So let's finish this proof of version 1. Okay. So so let's just recall what version 1 was. So remember, version 1 is that if fx and gx are two polynomials in Rx, where R is a UFD, then content of f times g is same as content of f times content of. Okay. So let's prove this. So fx is gx times hx, where f, gh are elements of Rx. So first thing we can do is write gx as content of g times some other polynomial gx, and hx as content of h times some other polynomial hx for some gh in Rx. Yeah, capital G and capital H in Rx, and then g and h has content 1 essentially. Yeah. So what we get is fx is content of g times content of h times gx times hx. Yeah. So of course, this content of g and content of h are elements of R. Yeah, and they will divide fx. So they will divide the content of f as well. Yeah. So we automatically get that content of g times content of h divides content of f. But we want to say the equality holds. Yeah. So say content of f, we can write it as product of irreducible, and content of g and content of h also we can write it as product of irreducibles. Yeah, because R is a UFD, and there is some uniqueness. Yeah. So in fact, what we can do is let's just slightly bigger. So let CG times CH equals and let's say P1 to Pn. Yeah, where PI's are in R are irreducibles. So we can, given any element of R, we can do this. Yeah, I mean this element is defined up to a unit, so is the expression. Yeah, so it doesn't matter. And since CG times CH divides CF, this implies that CF we can write it as P1 to Pn. So there will be some, so CF is CG times CH times something, yeah, and that again we can write it as some product of irreducible. So maybe Q1, Q2, Qm, yeah, for some m greater equals 0. So possibly there is no Q1 to, in fact, we want to show that m is 0 and Qis in R are irreducible. Yeah. So this is what we get from our conclusion that CG times CH divides CF. Yeah. So our objective is to show that m is indeed 0. So if we show that m is 0, then we are done. Then we would have shown that CF is same as CG times CF. Okay. So yeah. So suppose m is not equal to 0, then we'll get a contradiction, and then Q1 exists. Yeah. So now the point is Q1 will yeah. So what do I want to do? Yeah. So maybe I'll write down CF is let's say CG. So this and this identity CG times CH divides CF will get CF is CG times CH times some element. Yeah. So let's call this something D maybe. Yeah. Or some D in R. Yeah. Then what we get is that Yeah, so what do we get? So I want to basically cancel out the CG times CH and get something on the left hand side. Yeah. So so that exists so I have this. I didn't try. So maybe we'll take. So we would do something similar for F, like we did for G and H. Yeah. So also Fx, we can write it as some CF times capital Fx. So the idea is to reduce it to primitive polynomials. Yeah. So that's what I should have done for some Fx, not x. In fact, this capital F or capital G, capital H is also sort of unique up to a unit. Yeah. So we can always write this. Then this identity we get is that so what we get is that CF times Fx is CG CH times GX times HX. And now using this identity, we get that D times Fx is basically Gx times Hx. Where, so we also know that, so we have factored out the GCD of all the elements, all the coefficients of little g. Yeah. So what we get is that G and H are primitive. G, H are primitive. So that means, I mean, there is no common factor in the coefficients of G, and there is no common factor in the coefficients of H. Yeah. So the GCD is 1. Okay, so far so good. So let's just jot down everything. And D is Q1 to Qm. Yeah. So we want to get to some contradiction since we are assuming M is non-zero. Yeah. So of course Q1 divides Gx times Hx. Yeah. Then we will, if I show that Q1 divides either Gx or Hx, then we are done, right? That will contradict that G and H are primitive. That will say that one of them is not primitive. Yeah? So we'll do that. Yeah. So we'll show that Q1 divides either G or H. So let's take Gx is, let's say, BMx for M plus BM minus 1 x power M minus 1 plus B0. Okay, and Hx is CL x power L plus CL minus 1 x power L minus 1 plus C0. Okay. So Q1 is I mean, I'll just tell you verbally what this strategy is. So suppose Q1 does not divide B0 and Q1 does not divide C0. Yeah. Then of course Q1 will not divide B0 times C0, right? Because Q1 is irreducible in R and R is a UFD. So Q1 is prime in R. Yeah. So if it does not divide B0 and does not divide C0, it won't divide B0 times C0, which will contradict the fact that Q1 divides G times H, because the constant term of G times H is indeed B0 times C0. Yeah. So this is how the argument sort of goes. Yeah. So that is the base case. So So what you do is take the smallest term for which Q1 does not divide. Yeah, so let I naught be the smallest integer such that Q1 does not divide Bi naught. Am I still online? Yeah, can you hear me?
Yes, sir.
Yeah, okay, good. And similarly, let J naught be the smallest integer such that Q1 does not divide Cj naught. Okay, so that that tells you that all the smaller ones. So did yeah, so that means Qi naught minus 1 and so on. So B0 up to Bi naught minus 1 are all divisible by Q1. And C0 up to Cj naught minus 1 are all divisible by Q1. Okay, so that is what we are in this setup. Yeah. So now let's just look at so first of all, this will exist. Yeah. So note I naught J naught I naught is less than M. And I naught is less than M, less equal M, and J naught is less equal L. Yeah, because we have assumed that G and H are primitive. G, H are primitive. Yeah. So Q1 cannot divide all the coefficients. Yeah. What do we do? So now you just look at the term. So consider the coefficient of x power I0 plus J0 in Gx times Hx. So what is that coefficient? So it's going to be B0 C J0. Is that the right one to look at? No, not. Yeah, so this is not right. BI0 J0 I should write. Yeah, yeah. So this is the right thing to look at. I0 J0 plus B I0 plus 1 C J0 minus 1 plus B. So some of these B's may be 0, and B I0 plus J0 C 0. Yeah, and then there will be some terms in the other direction. So B I0 minus 1 C J0 plus 1 plus B0 times C I0 plus J0. Yeah. So note that consider the coefficient of this. Let's call this A. So note that Q1 divides A because Q1 divides Gx times Hx. Yeah. So by hypothesis, Q1 divides A. And of course, Q1 divides all the terms except the first one, right? Because Q1 divides Cj0 minus 1, all the smaller terms Q1 divides, yeah? Because J0 is the smallest one which Q1 does not divide. Also Q1 divides so maybe I'll write it in words rather than formulas. Divides all the terms except Pi0 Cj0, yeah. Hence Q1 has to divide this as well, right? So Q1 divides A and everything on the right except this term, then of course Q1 has to divide the difference. So Q1 divides Bi0 Cj0. This contradicts but Q1 is irreducible and hence prime, contradicts that Q1 is prime element of R as Q1 divides Bi0 and Q1 does not divide Bi0 and Q1 does not divide Cj0. But Q1 is irreducible element of in UFD irreducibles are prime, yeah. So that's it, yeah. So that completes the proof. So the contradiction came from the fact that we are assuming M is non-zero, yeah. So such a Q1 exists. Okay. Is that clear, everyone? Any questions?
Excuse me, sir.
Yeah.
Sir, I was just thinking of some other proof which actually was hinted in a text, but as an exercise. So I don't know if my solution is correct. Sir, if we consider the coefficients over here, we consider G and H are primitive because that's what we were studying later on. And suppose GH, the product is not primitive. Then if we consider the coefficients of GH and form an ideal using those coefficients, that would be a proper ideal of the underlying ring.
Yeah.
So we can say that the ideal like Jx, the ideal of the form, the coefficients with like the polynomials with coefficient in that ideal is also a proper ideal.
Sure.
So that is contained in a maximal ideal because we are assuming unity is in there in the ring because it's an integral domain.
Okay.
So if we consider in that maximal ideal, GH is in that maximal ideal by definition. But neither is G or H in that maximal ideal because both of them are primitive.
Polynomial, the coefficient. Yeah, so not maximal ideal, but coefficients are in maximal ideal. Yeah.
Yes, sir. We just treat it as the coefficients.
Yeah. So yeah, something like that. So somewhere you have to argue some trickery one has to use. Yeah. So, but yeah, so there may be other proofs. Okay.
Okay, sir. Thank you, sir.
Yeah. So here also basically what we are showing is, so we are showing that G times H is not primitive, is also primitive. So we are assuming that if Q1 divides G times H, so to show that G times H is primitive, we have to show that no irreducible element divides it. Yeah. So let Q1 be an irreducible guy which divides G times H, then you get some contradiction. Yeah, so that is what we have done. So all the step before this is to just reduce it to primitive case. And then this last part is to show that show the case when G and H are primitive. Okay. Any other question? Okay, so maybe we'll stop here and we'll see some applications next time. Okay.